Today we are going to solve the problem 1.15 and 1.16. First we will see the problem 1.15. The problem 1.15 is so that the time derivative of integral of minus infinite to plus infinite psi 1 star psi 2 tx is equal to 0 for any two normalizable solution to the Schrödinger equation with the same potential V of x, psi 1 and psi 2. So you can take by definition the time derivative we have to find from the problem time derivative of integral between minus infinite to plus infinite psi 1 star psi 2 dx is can be written as you bring the full derivative inside the integral. See, this is the number, you know very well, this is the probability. So it's a number. You can differentiate with respect to time. But when you bring this time derivative inside the integral, this wave function depends on the position also. So this will become partial derivative. That is partial integral between minus infinite to plus infinite, partial derivative with respect to time, psi 1 star psi 2 dx. So now you can write this right hand side, that is minus integral minus infinite to plus infinite delta over delta t psi 1 star psi 2 tx is can be written as first you differentiate psi 1 star, then you keep psi 2 as it is, then you keep psi 1 star as it is and differentiate psi 2. So this will become the integral between minus infinite to plus infinite, partial time derivative of psi 1 star multiplied by psi 2 dx plus integral between minus infinite to plus infinite psi 1 star partial time derivative of psi 2 dx. So we will take this and move further. Now we have to find this integral. Uh, Take the Schrödinger wave equation. Uh, See, in this problem, it is given that the potential is same for pi, psi 1 and psi 2. So instead of removing the potential at the end after some mathematical step, at the beginning itself we will cancel out the potential because potential for psi 1 and psi 2 are the same. So let us consider the Schrödinger wave equation I h cross delta psi over delta t is equal to minus h cross squared over 2m delta 2 psi over delta h2. That means if you bring this I h cross this side, this will become minus I over h cross. So minus I over h cross when you are bringing this I h cross. So minus of minus will become plus and h cross will get cancelled with this h cross squared. So this will become I h cross over 2m times delta 2 psi over delta x2. This is the now my aim is, see, inside the integral I want to bring all the terms in terms of x. So here time derivative I want to bring this in terms of spatial derivative, that is dx. So you just replace uh, time derivative of psi 1 star, then it will become, see, this is the complex number. So when you take the complex of minus I h, complex of I h cross, it will become minus I h cross over 2m. So I am taking, since it's a constant, I am taking outside. This minus comes because I will become minus I if you take complex conjugate. Then uh, I'm this first order time derivative will become the second order partial derivative. Of course, this psi 2 I am keeping as it is. Similarly, in the second term, This will be psi 1 star. This is not a complex number, so I am taking as it is. So this will become I h cross divided by 2m delta 2 psi 2 over delta x2. So I have rearranged all the term inside the integral is x dependent. So I have converted all into x dependent. Here you can see, since it's a constant anyway, finally we are going to remove. We will use it if required. Otherwise, you remove this IH cross divided by 2m, not this sign. Here it is minus, here it is plus. Now you take this minus, this second order partial derivative will become d by dx of d psi 1 star over d psi, sorry, dx. So the psi 2 will become as it is. Similarly, here the second order derivative I am writing like this. That is t by tx of t psi 2 over tx2. So this is the integral I have split into. Now you take care of this by integral by parts. That is, you take this as u, and that is psi 2 as u here, and this partial derivative with respect to x is v. That is delta psi 1 star over delta x is v. So we know that integral u dv is equal to uv minus integral v du. So here first term is uv. Here u is psi 2. B is the partial derivative of psi 1 star with respect to x. So between the limit minus infinite to plus infinite. Uh, so I will come to it later. Then next, uh, minus minus of minus will become plus here. Plus uh, V du. V is t psi 1 star over tx, and du is t psi 2 over tx. So this integral will become two part if you are integrating by parts method. Then this one, second integral, you take second integral. This is u, that is psi 1 is u, and this one t is psi 2 over tx. This is dv u dv. So this integral become u dv. This is v u dv. So which is equal to u is psi 1 star, and v is t psi 2 over dt. So between the limit minus infinite to plus infinite, minus v du. Here v is delta psi 2 over delta x. V du is this one, psi 1 star. T is psi 1 star over tx. So now we have to prove this value. You take the first term. The wave function must vanish at infinite. So this will become 0. And also here also the same thing. Wave function psi 1 must vanish at infinite. So this is also will become 0. You take second and fourth term. This is plus partial derivative of psi 1 star psi 2. This is minus the partial derivative of psi 1 star psi 2. So both will get cancelled because this is plus and this is minus. So naturally you will get 0. So we have proved that the time derivative of the integral minus infinite to plus infinite, psi 1 star psi 2 dx is equal to 0. Now we will move on to the problem 1.16. The problem 1.16 is a particle is represented at time t equal to 0 by the wave function psi of x and 0 is equal to a multiplied by small a squared minus x squared between the limit minus a to plus a, and it is equal to 0 otherwise. This problem consists of 8 parts. We will solve one by one. First you take section A, determine the normalization constant. So to determine the normalization constant, we have to integrate between minus a to plus a psi star psi tx. So psi star psi is because it's a real number, so we can square it. So a square integral between minus a to plus a squared minus x squared whole squared dx. Now you change the limit from 0 to a. So you have to multiply this integral by 2. So this will become 2a squared integral between 0 to a squared minus x squared whole squared dx must be equal to 1. Now you expand this a squared minus x squared whole squared, which is equal to a power 4 plus x 4 a squared, that is a squared plus b squared minus 2ab, that is a power 4 plus x power 4 minus 2a squared x squared dx. If you integrate this, uh, you will get, it's a straightforward integration, you will get a squared is equal to 15 over 16 a power 5. That means a is equal to square root of 15 divided by 16 a power 5. This is the very simple integration, so you can carry out easily. Now section P is what is the expectation value of x, and section C is what is the expectation value of P. Note that you cannot get it from expectation value of P is equal to m multiplied by time derivative of expectation value of x. Why not? We have to answer that also. So the expectation value of x is equal to psi star x psi, that is between limit minus a to plus a x modulus psi squared dx. See, this is the odd integrand. X is odd number. So naturally this will be 0. So expectation value of x is 0. What about the expectation value of p? You apply the same rule, psi star p psi tx is equal to, now I am replacing this uh, p by its operator, that is p by its operator minus I h cross t by tx. This is the uh, replacement for momentum operator. Here the psi star psi is equal to a square, that is square of the normalization constant, and integral between minus a to plus a square minus x squared, and first order position derivative of the wave function a squared minus x squared. So if you differentiate this once, you will get, if you differentiate the constant with respect to x, it is 0. So you will get simply minus 2x. Here you can see x also, again this is also an odd integrand. This is of course even. So I add integrand, so naturally it will be 0. The specific question asked is, why can't we use m multiplied by time derivative of expectation value of x? We cannot find a time derivative for the expectation value of x because the given wave function is at t equal to 0. We cannot calculate it using time derivative of expectation of x directly. So that is the reason for the same. Section D and E is find the expectation value of x squared and expectation value of p squared. First, we will solve the section T, that is the expectation value of x squared, which is equal to a squared x squared psi star psi. So psi star psi, we know this is a squared minus x squared whole square. If you expand this and multiply by this by x squared, then you will get a power 4 x squared plus x power 6 minus 2 a squared x power 4 tx. Here we have seen a squared is equal to 15 over 16 a power 5, and we are changing the limit from minus a to plus a as 0 to a, so that multiplicative factor 2 comes here. So if you integrate and apply the limit, you will get the expectation value of x squared is equal to a squared over 7. Because it's a very simple integration, I have taken the result as it is. You can easily carry out this integral. So now section E is find the expectation value of p squared, which is equal to the momentum squared operator is minus h cross squared t2 over tx2, and this is psi star. This one is psi star. This is psi star, and this is naturally the psi. So if you can replace a squared by 15 over 16 a power 5, and this 2 comes because we are changing the limit from minus a to 0, 0 to a, so 2 will come here. Then if you differentiate this twice, if you differentiate this, I can change the color. That is, if you differentiate this twice, if you differentiate once, then this will become, if you differentiate a squared, this will become 0. Then this will be equal to t by tx of minus 2x. If you differentiate this again, then you will get minus 2. That's what I have written here. So this minus of minus will become plus, and this 2 will get cancelled with this 16, which will become 8. Now you have to integrate a squared minus x squared with respect to x, and if you differentiate and apply the limit, you will get 5 h cross squared over 2a squared. Then we will move on to section F. Section F is find sigma x. By definition, it's equal to square root of expectation value of x squared minus expectation value of x whole square. This will be 0 because expectation value of x is 0. Then this will become square root of expectation value of x squared, which is a squared over 7. So if you take square root, a squared will become a, and square root of 7. Then sigma p is equal to, by definition, square root of expectation value of p squared minus a expectation value of p whole squared. So expectation value of p we have seen is 0. Then this will become simply square root of expectation value of p squared. So which is equal to, just now we have seen, 5 h cross squared over 2a squared. Here h cross squared will become, if you take square root, h cross squared will become h cross, and a squared will become a. Then inside the square root you will have square root of pi by 2. Now we have seen the g, that is uncertainty of p, that is sigma p. Now we have to check the uncertainty sigma x into sigma p. Sigma x is a divided by square root of 7, and sigma p is equal to h cross over a square root of pi by 2. This one, square root of pi by 2. So naturally this a will get cancelled. So what I am going to do is I will bring this 7 inside. So that is 2 multiplied by 7, pi divided by 2 multiplied by 7. Now what I am going to do is uh, you multiply and divide by 2. That is this 5 will become 10, this 2 will become 2 square uh, multiplied by 7. So 2 square will become 2. So this will become h cross over 2, then square root of 10 over 7, which is definitely greater than h cross over 2. So we have checked the uncertainty principle also. Subscribe to my channel to get my latest videos, and join my channel to support its growth and enjoy the exclusive perks. Also use the thanks button to make one-time contribution and support my channel. Thank you very much.